Hello, everyone, and welcome back to our series on knowledge tracing. Today, we're diving into a fundamental and incredibly powerful machine learning model, the decision tree. If you've ever wondered how a computer can ask questions to figure out what a student knows, this video is for you. We'll break down the entire process step by step using a simple example. Let's get started. Before we jump into decision trees, let's talk about a big challenge in modern AI, especially in education. Models like deep knowledge tracing, DKT, are incredibly accurate at predicting student performance, but they're often called black boxes. We get the answer, but we have no idea how the model arrived there. This is a problem for teachers and educators who need to trust and understand the AI's reasoning. What if there was a model that was not only accurate, but also completely transparent? That's where decision trees come in. So, what exactly is a decision tree in the context of knowledge tracing? Let's use a simple analogy. Think of it as a super smart teacher who plays a game of 20 questions with your students' data. Instead of looking at all the information at once, it asks a series of targeted questions. For example, it might first ask, has the student answered more than 2 linear equation questions correctly in the past? Depending on the answer, it asks another question, like, did they get the last one right? This process continues until it reaches a final conclusion. The magic behind a decision tree is a process called recursive splitting. Recursive means it repeats the same action over and over. Splitting means it divides the data into groups. The tree starts with all the students and asks a question that best splits them into 2 groups, those who know the concept and those who don't. Then it takes each of those new groups and asks another question, splitting them further. It keeps doing this until the groups are so pure that it can make a confident prediction. To decide which question to ask at each split, algorithms use mathematical criteria like information gain or the Gini index, which measure how much the split improves the purity of the resulting groups. Let's look at the first metric for choosing the best question: information gain. The idea is simple. Before asking a question, our data is a mix of students who know the concept and those who don't. This is chaos or entropy. A good question should reduce this chaos significantly. Information gain measures exactly that, the difference in chaos, entropy, before and after asking the question. The bigger the drop in entropy, the more informative the question is. The second metric is the Gini index. Think of it as a measure of purity. A group where everyone is the same, all masters or all novices, has a Gini index of 0. It's perfectly pure. A group that's a 50-50 mix has a Gini index of 0.5. It's maximally impure. The formula calculates this. When we split the data, we calculate the Gini index for each new group, take a weighted average, and see how much it decreases from the original group. The question that gives us the lowest weighted average Gini is the best one to ask. All right, enough theory. Let's get our hands dirty and build a decision tree from scratch with a small example. Imagine we have 8 students. We have 3 pieces of information or features about each student. Their past success with linear equations, whether they got the last question right, and how long they took to answer. Our goal is to predict if they will get the next question right, labeled as 1, or wrong, labeled as 0. In our data set, 5 students got it right and 3 got it wrong. Step 1 is to calculate the impurity of our starting group, the root node. Using the Gini index formula, we plug in the proportions of know, 5/8, and don't know, 3/8. The calculation gives us a Gini index of approximately 0.4688. This number represents how mixed up our group is. Our mission is to find a question that will split this group and lower this Gini score as much as possible. Let's test our first feature, exam. Has the student answered more than 2 questions correctly? This splits our 8 students into 2 groups. The left group has 6 students. 5 of them know, 1 don't know, giving a Gini of 0.2778. The right group has 2 students. Both don't know, which is perfectly pure with a Gini of 0. We calculate the weighted average Gini for this split, which is about 0.2084. Compared to our starting Gini of 0.4688, this is a reduction of 0.2604. Not bad. Now let's test the second feature, X2Z. Did they get the last question right? This splits the students into 2 groups of 4. The left group, who answered correctly, are all no, so their Gini is 0. The right group, who answered incorrectly, has 1 no and 3 don't know, with a Gini of 0.375. The weighted average Gini for this split is 0.1875, leading to a Gini reduction of 0.2813. Comparing this to the reduction of 0.2604 from the first question, we see that X2 provides a more significant reduction in impurity. This means asking about the last attempt is a more powerful first question to maximize information gain. Therefore, our decision tree will start with X2 soon. Our tree's first question is last attempt correct. If the answer is yes, we can confidently predict the student is no. That's a leaf node. But what about the no branch? This group of 4 students still has some impurity. Gini equals 0.375. We need to ask another question here. Let's try X3. Did they take a short time? This splits the group perfectly. The student who took a short time is no, and the 3 who took a long time are don't know. Both new groups have a Gini of 0, so we stop here. These are our final leaf nodes. And there we have it. This is our final decision tree. It's a simple flowchart. Start at the top. Did the student get the last question right? If yes, predict they know it. If no, ask a follow-up. Did they take a short time? If yes, predict they know it. If no, predict they don't. This clear, interpretable logic is the beauty of decision trees. So, what exactly is the decision tree learning when we train it? It's not learning weights like a neural network. Instead, it's learning a set of rules. It learns which feature to split on at each node, the exact threshold for that split, like Y2 is the magic number for correct attempts, and when to stop asking questions, which is controlled by the tree's depth. The entire goal of training is to make the optimal choice at each step to maximize the purity of the resulting groups. In a real KT system, a decision tree would take in a rich set of student data as input, such as their history, performance, and time spent on tasks. Its output is a probability of success on the next question. The biggest advantage is its interpretability. Educators can see exactly why a prediction was made, which is critical for trust. It is also easy to implement. However, a single decision tree can be unstable and prone to overfitting to noise. That's why we often use more advanced models like random forests or gradient boosting, which combine many decision trees to get a more robust and accurate prediction. To wrap up, decision trees offer a fantastic balance of performance and interpretability for knowledge tracing. They solve the black box problem by providing a clear, logical path to their predictions. As we move towards more trustworthy AI in education, models that we can understand and explain will be more important than ever. Thank you for watching, and stay tuned for our next video.